Thank you. Yeah, welcome everyone. Hope you all had a good weekend, long weekend if you had that. Right, let's make a start. So I'll share my screen and I'll turn off my camera because sometimes that gives problems. Okay, now this week we're going to start looking at Rust, and it's going to be quite a gentle introduction. And yeah, so tomorrow it's going to be quite practical as well. So yeah, tomorrow it's not going to be a problem that we have a little less time. So what it will be is I'll just go through some details of the language, for really to start from scratch, particularly for those of you who haven't worked in Rust before. And then we have some practical work to do, and you'll be able to do that in your own time. I know you have the other homeworks as well, so you should have plenty to keep you busy. So I'll start off with an introduction to the language. It's a it's a relatively recent language as languages go, and it was designed with some features in mind, drawing on, I think, some of the problems that other languages had. And one of the really outstanding and innovative features of Rust is the idea of the memory safety without garbage collection. So if you've worked in other languages, you'll know that this can be problematic, that the either you have you have to sort of work out the memory safety yourself, and by that I mean you have to handle what items in memory are being used by a program at a particular time, and what can you safely overwrite and what shouldn't you be overwriting. Um, doing that yourself is a big overhead. And then the approach that languages took to make that easier was the idea of doing some handling of that within the language or within the whatever framework of virtual machine, something like that. And if you do that, then they tended to use this idea of garbage collection. So they would handle the memory for you and free up pieces of memory. But this had to be you had to have an idea of a garbage collection to run to make sure that the areas of memory that were allowed to be used that were no longer needed were marked as such, and it was done in a safe way. And if you've worked with languages like Java, you'll know that this, I mean, even though it was done in a very clever way, the garbage collection, and has improved over the years, it still can cause performance problems at time, and something that not everybody really likes. So that is something that Rust was trying to solve, and it has done it in a quite a unique way, in that it tries to make sure that the compiler can work out what is happening with memory and can enforce the memory safety. Rather than having to do this at runtime, the compiler can get involved in this as well. And then the other idea that kind of goes hand in hand with that, I suppose, is the idea of concurrency without data races. So the idea that you can have multiple threads in your code that can run safely, and their interaction will be done in a safe manner. That's either you don't get either them interfering with each other's objects or memory, or the other thing is that you don't get kind of deadlocks where everybody is waiting for another thread to do something. And another idea they have, this abstraction without overhead, I think came from the problems that C++ has with, or some of the approaches to generics. It's often difficult to get that quite right. You often end up sort of building sort of kind of too much code into that. But we'll come on to generics in a later lesson. But these are some of the features that sort of drove the development of Rust. And it's really aimed at being a very efficient language, and being a system language as well. It can be used in embedded coding as well as more general code. So Yeah, a lot's gone into Rust, and this we will see how some of these aspects do influence how the way the language is designed, particularly the ideas about memory safety and the what we have to do as programmers in Rust to comply with that. But today we'll just go over some very straightforward, some very easy aspects of the language. So I'm just going to go through just generally explaining the syntax, and if you have questions, please do put them into Slido so we can answer them there. So the first thing, I mean, variables, the same as you would normally expect. You declare them by using the let keyword, and wherever this is done, we'll define some scope for a variable. But one thing that Rust has in common with some functional languages is the idea of mutability of variables. So by default, variables are not mutable. So having once initialized a variable, then that cannot be changed. If you want that variable to be mutable, then you use the mute keyword, as you can see on the second line there. So that means that you can then change the value of y further on in the program. So we'll have a look at some of the types. It is a typed language, so we do need to give the compiler an idea of the types we are using. But the compiler can be quite clever with this, so it may well be able to infer the types of the variables that you are declaring, if it has enough context to be able to do that from other things that you have done. So if you've created a variable of one type and then you've put that into a variable, then it will know that it is going to be, it should be of the same type, for example. So there are these scalar types, which I think these are all straightforward. You will understand what these mean. Integers, yeah, I think that's sort of self-explanatory, really. The whole numbers can be positive or negative. Floating point numbers allows rational numbers, so we can have decimals. Booleans are true or false, and then characters are single characters representing some text. So integers, we have an example here. You specify the size of the integer that you want, or it can the compiler can make a guess at that type if you're not specifying it, if you're using a literal, for example. So the ones I've got here are just the number of bytes that are involved. It's the U or the I is for unsigned, or I is for integer, signed integer. So they allow positive and negative values. Floating points, you have to use the F in front of the to denote that, and you also can specify the size. So again, the number of bits that are that you want in the variable. It's and they're all signed. I think the defaults are F64 because that gives you more precision, and I think most CPUs are going to be capable of doing that. Obviously, for some applications that might not be the case, but on the whole, with what we're doing, that probably is going to be feasible and available. Booleans, true or false. I don't think I need to say much more about that. So usize, this is something where you does take into account the hardware or the operating system you're on. So usize is pointer size, and the architecture you're on. So this does depend upon what you're compiling for. So if you are on a 32-bit system, then usize will be 32-bit, and on 64-bit systems, usize will be 64. So this is useful in that it gives this guarantee there that you won't be trying to use something that your architecture won't be able to cope with. Yeah. And then compound types. So going away from the simple types, we can put types together to produce something more useful. So tuples, yeah, these are like tuples in other languages, and they have a similar syntax. You can mix the types for those, and you see some examples here. If So in the top line here, the way we have the let x, we're specifying the types of the values that we have in our tuple. So the first one is a 32-bit unsigned integer, signed integer, and then the next one is 64-bit floating point, and then an unsigned 8-bit integer to finish with. If you can pull them out, you can denote which one of which part of a tuple you want by using dot notation. So as you see in the those examples there, the dot 0 means we're taking the first one, and the dot 1 is the second one, etc. So fairly straightforward. Structs, I'll come on to arrays later, but structs, similar to structs in other languages, it allows us to build up an object which contains other types, and this is useful. This is more of a kind of a business use that you will have for this. So this will be dependent on your program. You will want to create an object of a particular type because that makes some sense in what your application is doing. So here we have an example with a user, which is and the user will have a name, an age, and an email, and the reason we've got some details of the size here is that the size of the structure as a whole may be different to the sizes of the primitives that go into it. I think so it can be larger than the size of the primitives. That's the only reason for those comments there. Okay, so yeah, I'll come on to arrays in a moment. But that's some of the sort of more the basic types. We'll go on to things like enums tomorrow. But anyway, that's some of the useful types that you need to be getting on with. Loops in Rust, again, these are quite similar to what you will have seen before, and the useful syntax. You can use similar syntax to you have in other languages, and this you have this idea of the inclusive starts and ends. You can specify that. So you can do this, use this for, and then a variable in, and then a particular range. So the two loop types we have are the range and the collection type here. So the range type, we do the simple for some variable in, and then we can specify a range, and you can also do a step value, again, similar to what you expect in other languages. And then the other type, if it's not a range type, is a collection type. I won't go into vectors today, but this is similar to collections in other languages. So you can if you have something like this, then the loop can be created from an iterator, and we'll go into those again. I think that'll probably be tomorrow as well. So because with collections, the collection itself knows best how to go through a particular collection. So with a collection, we use an iterator to then iterate through them. Strings are similar to what we have in other languages as well. With ASCII mappings for characters, and use UTF-8 encoding. If we're using chars, then that's a unique value that represents a Unicode value. But do be aware that you don't treat this as a numeric type as you do in some other languages. So don't try to do that. But there are ways to specify this to get different Unicode code values if you need to. And there's plenty of documentation around that. I'll give some examples later, I think, of string literals, of literals where we, character literals where we do this. Strings are a little bit more complex, as well as in most languages. There are sort of, you can look at them in two ways. The first way shown here is if you see them as a sequence here of some bytes, but you're really just pointing to the first byte. So if you use this approach, you then is unalterable. You can't really change what is actually within effectively this array. And then string, the more user-friendly type, is growable and mutable for that, and will give you also know the capacity of that. Obviously, when it's being stored in memory, it has to know the capacity, so you can do that. And yeah, you can see the string literals if they, in common with other languages, for performance reasons, these will be stored at compile time in the binary, so you can often see these. Okay. This is just a screenshot to show you the difference between those two types. And so, yeah, the example, if you have something like fizzbuzz is as a literal, then that's a reference to something encoded in the binary. And you can use a toString method to convert to string. There's more details about that in the links there. I just wanted to mention strings briefly now. We will go over them in some more depth in later lessons, but it's useful just to have them because people use them, particularly literals, when they're first writing in Rust, so it's useful to get those mentioned. And then arrays are similar to arrays in other languages. So they're a set of objects of the same type. So here where you're saying type T, and you can do generics here, but we won't go to that sort of complex thing, but they will be of the same type, stored in contiguous memory. So the use of arrays can have performance issues. Sorry, not in a bad way. They can be good for performance because the CPU, when it is running, generally likes things to be contiguous. It allows the CPU to do all sorts of optimizations and to cache things and to prefetch things. So using arrays can be quite good for performance. So yeah. You create them using the bracket syntax as you do in other languages, but they are static, so you cannot resize them once they have been initialized, and they use an index. Again, I think this is all obvious and straightforward. And well, one thing is, though, you cannot elements within the array cannot be deleted. So you can update or modify various elements, but you cannot remove them from the array because you cannot resize the array. So there's some examples here of the declaration of arrays. So you can, if you don't specify the type, the compiler should be able to work out the type for you. So for in this example, it would know the type because we're applying literals. You can specify the type involved and the size of the array. So there's an example there where we're specifying these are I32. And we want 5 of them in our array. We can specify a default value for the arrays, for the elements within the array as well. So in this next line here, we've got integers. We've said that there are going to be 3 of them, but we're putting in a default value for these of 0 here. And then in the same way that our variables can be mutable or immutable, and we have the same thing with arrays. So you can say, you can use the mute keyword in front of the array to say that this array is mutable, i.e. you can change the values in this array, or if it's immutable, then you can't do that. Okay. Slices, yeah, I think these are common to most languages, but if you haven't come across them, they're really a kind of like a subset of an array, or you can often think of them as like a kind of a moving window moving across an array. So you can take, if you have an array, a set of items that are there in memory, you can take a slice of those, which means you take a subset of those items and have that as a slice. Because quite often when we're operating on items, we don't want to have to operate on the whole thing every time. We just want to operate on parts of that. So it's useful to be able to take a slice. And there are some links there to details about that. Okay, and we'll have examples of all of this. So we'll go through in the practicals and in the homework with doing examples of all of this. Just to talk about literals, so starting with numeric literals, usually the compiler can work out the type of the data type of a literal when you're declaring it, so you don't always have to say the type. But if there's a choice of the type, if it's not obvious which it should be, then it will default to I32, which is a reasonable default. I think that's often what you would want to have as the type and size of an integer. If you want to specify that something is hexadecimal or octal or binary, then you can do that by adding prefixes to your literals. Again, you probably come across this before, so you can have 0x, 0o, or 0b to show that they are those types of literals. And what a nice thing too as well to make your code more readable is that you can use underscores, so to group numerals together to make the whole thing easier to read. So that will be understood, and it just makes your code more readable. So that's numeric literals, ASCII code literals. You can use byte literals for that and then put them in single quotes to show a specific ASCII code. There are other ways of doing that, more complex ways as well, but we don't need that for the moment. But there's examples in the links I've given if you need to do that. And then conversion between types. So Rust, I think, is different to many languages in that it does less implicit conversion between types than you might get in other languages. So it does force you to be specific, to be explicit about conversions if you're going to do them. If you want to do that, you can use the as keyword. So the example here. So you can move from the type of A, which is going to, I think that's going to be defaulted to be an I32 here, and then you could move that to a usize, as shown there. So if you want to cast between types, then you usually have to be explicit about that. But obviously the compiler is there to pick you up if you're not doing this kind of thing as it expects. So, okay. Then just a brief introduction to functions. You start them with the fun keyword. The syntax should be very familiar to you. We have a function name. We have parentheses in which we can put in the parameters, and we put in the name of the parameter and specify a type for that. And then we specify a return type from the function. So here our function is going to return the ball. And then we have curly brackets for the function body, and then whatever code or whatever statements we want to have in the function itself. And you'll note here that whereas mostly we're ending our lines with a semicolon, the final line here in this function is not ended with a semicolon, doesn't have a return either, because if we have this as a statement as the final line in the function, that is assumed then to be the return from the function. So this is supplying the ball from this function. And it is typically we use this pattern. We would use the return keyword when we're returning before the end of the function rather than at the end of the function itself. One thing you're going to want to do when you're starting out is to print out some values so you can see what your code is doing. And for this, we use what is called a macro, and a particular one, the print line macro, as you can see here. There are different ones. This one gives us a end of line at the end of our statement. And as you see here, we can print out string literals. There are different ways to format if you want to print out different things. This next pattern here is one that is fairly useful and will cope with most data types. So what it is doing within the curly brackets here, this is really a placeholder for some value. It may be a literal in this case, or it could be some variable that is going to get printed out, but that is then within our larger string that we are printing out. So this final example here would be printing out 19 tokens. Yeah, so it would be in that way. And if you have more, then you would specify them going on there. Yeah, the semicolon I explained. The question about that is just because it's the last line in the function, so that acts as a return. Now, that's really all. I think all of the kind of the syntax you need to start using Rust and to start to get some practice with it. So I'll just go through what you need to do to install it. The easiest way is via this thing called RustUp. And if you're on Mac or Linux, then you can just run this command and this will install Rust for you. Windows, it's a little more complex, but there's links there to do that, and it will give you an executable that you can use to do the same thing, to install Rust on your system. If you have other systems or very specific requirements, there's a link there to the other methods. So the best way to go now, the best way to learn all of this obviously is to use it, to try it out. So what you can need to do next is to first of all install Rust. So either you can do this on your system so that you'll have it so you can develop locally, or if you prefer, you can use Gitpod. So we've given we had a repo last week, and we've got another one in Homework 5 that you can use for that. So I'll just go through Homework 5. So I don't know why that's not scrolling to the top, but anyway. So first of all, you need to install Rust. Again, a link to the instructions. We've supplied this repo for you to use, and this repo contains exercises for you to go through. Now, we've taken these from a project called Rustlings because that's a really good way of going through and learning, and sort of it takes you by the hand and lets you learn all of the aspects of Rust in a really structured, nice way. So what we've done is we've customized that to take you through and build that out into a to correspond to the lessons we have. So the first homework we have here will correspond to what we've covered in this first lesson. So you can clone that repo, or you can open that in Gitpod. And open a workspace in Gitpod with that repo. Either one is fine. Then to install the libraries that you need, we use the Rust package manager called Cargo, which I haven't explained this so far, but we will in later lessons. But just for the moment, you just need to run that command, and that will install everything that you need to run this particular exercise. And then when you've done that, when everything's installed, you use the rustlings command and then specify homework and then specify 1. And as we go through the homeworks, we'll change this number so it goes through and does different numbers. And then just follow the commands that gives you, and it will show you what you need to do. You need to get things to compile. It gives hints as well if you need help. And then once you're done, you can take out the I am not done file and go on to the next item. But that really should be all self-explanatory. You can just follow the instructions that are there in the repo. Yeah. So for today, yeah, that's the practical session, and we'll just introduce more exercises into that repo each day for you to go through, and these will correspond to the pieces of theory that we've done in the lessons as we go through Rust. So please get on with that. If you have still to finish the homeworks from last week, then obviously you can also do those. But yeah, please try out that, install Rust, and then go through those examples. If you have questions or any problems, then please put your comments into Slido, and we'll help you out. And I'll help you out with that. Yeah, so that's it. As I said, it's just a short introduction to Rust there. It's mainly a practical session today because the best way to learn is by doing. So we want you to make a start on that. But yeah, if you have any questions, then please ask. Otherwise, we'll just wait here for the rest of the lesson. Thanks, everyone.
Lawrence, are you around?
I am, yeah.
Cool. Just had a quick question. I am running into some build errors on step number 3.
Okay, I think. All right. Can you put details into Slido? It's easier to work out from there, I think.
Sure.
Yeah. Thank you. I think, but also in chat, if you look in chat, some people had some errors.
Yeah.
So I don't know if that might be useful. But anyway, if you put the details in Slido, then we can give you a better answer for you. Thank you.
Sure. Thanks.
To save time, you have to try it in Gitpod. It's going to be difficult for me to try and reproduce this, I think, because you're using Windows. It's not going to be easy for me to reproduce that, but I'll keep looking at that. But I've just managed to run it okay in Gitpod. So do you want to try doing it there? And that will mean you can get on with it rather than having to wait.
Yeah, that's a good idea. Where do I find that again, the Gitpod stuff?
So what you need to do is if you take the repo, so the HTTPS, etc., and then in front of that, if you put Gitpod, let me just .io. Let me just write this out. Make sure I get this correct. Yeah, so gitpod.io / and then a hash, and then the rest of the URL. Okay. But I think in one of the previous homeworks we've got an example of that. So have a look back on the previous homework.
Yeah, I think I could pull up the previous homeworks pretty fast. Let's see.
I put a well, that's a different. It's a different repo actually for the previous homework. So let me just. I'll write out what you need to do.
Oh, I see. Yeah, okay. Gitpod.io. Okay, yeah, I think I see it in the URL. If I don't open the file. Your audio is cutting out a lot, Lawrence, but I got your reply and I got the Gitpod opened up now.
Hello, everyone. It looks like that will be kind of the end of our session for today. Just kind of a reminder, if you haven't looked at my message in Discord, we're going to have Class B first, the AMA with Robert Young. I think that is his name. And then we'll actually have class right after and do kind of this practical work again. So just check that. Please register and show up to the AMA first tomorrow. I edited the calendar invite to start after, so it should be edited in everybody's calendar correctly now. So just look out for that. Yeah. Lawrence, do you have any words?
No, just thanks everyone for joining today, and look forward to speaking to you tomorrow. Thanks.